This is a Math 2 lesson summary video for the task titled I Rule. This is a Solidify Understanding task. The purpose of this lesson is for students to create multiple representations of functions and understand the similarities and differences between linear and quadratic functions. In this task, you start off with a diagram that has 4 different figures. And we're going to get started by marking the diagram to show the rate of change and relationship between the number of blocks and the size number. And we'll create a table, graph, and equation. When I look at this diagram, the first thing I'm going to do is I'm going to record how many blocks are in each figure. I can see that when I'm going from one size to the next, I'm adding 5 blocks each time. It looks to me that the 5 blocks that I'm adding it's adding 1 on each end plus 1 in the middle. So the 5 blocks that are added to this figure, so I'm modeling recursively. I'm looking at how I'm going from one figure to the next. So recursively, what's happening is to get to the next figure, I take the previous figure and I add 5 more blocks, and I am starting at, with size 1, 7 blocks. So I have a recursive equation and a recursive relationship. I'm going to go ahead and show the table. So the table is just organized here where x represents the size number and y represents the number of blocks in the figure. And then if I look at that graph, here I have a graph where it shows my linear relationship. Now I know this is a linear relationship because if I look at the first difference, I notice that I'm adding a constant value every time, so plus 5. So my recursive rule shows this plus 5, my table shows this plus 5, and if I look at my graph, I can see that there's a constant rise of 5 units and a run of 1. So in addition to looking at my diagram recursively, I also want to look at the diagram and create an explicit equation. So I'm going to clear my diagram so that we don't get confused. And I want to relate the number of blocks in the diagram to the size number. When I look at the diagram for size 1, I notice that I have 1 block here, 1 block here, 1 block there, 1 block here, and 1 block here. So I have 1, 2, 3, 4, 5 groups of 1 plus 2 extras. Let's see if the same relationship happens when the size is 2. So now I'm looking for groups of 2. So there's a group of 2. Here's a group of 2. There are 5 groups of 2 plus 2 extra blocks. Here I have 5 groups of 3 plus 2 ones and 5 groups of 4 when the size is 4. So remember, with explicit equations, you want to try to use your size number. So since my size number is 4 here, I'm looking for groups of 4. So if I have 5 groups of 4 plus 2 other blocks. Here I have 5 groups of 3 plus 2 other blocks. 5 groups of 2 plus 2 other blocks, and then 5 groups of 1 plus 2 other blocks. So if my size was n, I would have 5 groups of n blocks plus 2, which means my explicit equation, now I'm going to use x, is f of x equals 5x plus 2, because whatever x is, whatever the size number is, I can multiply that by 5 because there'll be 5 groups of that many blocks plus the 2 extras. So this is a linear pattern. Again, I know it's a linear pattern because I have a constant rate of change. The graph makes a straight line. With my recursive equation, I'm adding a constant And in my explicit equation, the highest exponent that I have with x is 1. So its degree is 1. Its power is raised to the first power, so it's x to the 1. So I know that this is a linear equation. Let's take a look at the next diagram. In this diagram, so far I have 3 figures. I'm going to start by writing down how many blocks are in each figure. So this time when it changes, it's going up by 21 and then up by 35. From here, I'm going to go ahead and create a 4th diagram so I can get a little bit more data to work with before I start trying to create my equations. So I'm noticing that this size number, when the size number is 1, I have, this is 1 unit long, and this one is 1, and the middle part is also 1. For when the size is 2, I have 2, and then this is also 2, this one is 2, that's 2, and that's 2. And then it grows here, it's 3 by 3. I think I can almost even make a square right here. This one is 3 by 3. This one is 3 by 3. Now that I'm looking at this, I'm always trying to see if I can find a relationship between my size number and the diagram to help me later on when I'm wanting to make my equation. And I've noticed that this breaks up into squares, where the square's length and width is the same as the size number. So I noticed that size 1 has 7 squares that have a length of 1. Size 2 has 7 squares that have a length and width of 2 units. Size 3 has 7 squares that have a length and width that are 3 units. So when I create my next one, I need to have 7 squares that have a length and width of 4 units. So I have the area of each one, so that one has 16 blocks, and I have 7 groups of those. So to figure out how many blocks there are, I'll do 7 times 16 and get 112. And I notice that when I go from 63 to 112, I'm adding 49. I'm going to go ahead and look at a table of values and the graph for this. So I can see that this is definitely not linear. I do want to look a little bit more closely at this table so that I can figure out if this is indeed a quadratic function. So I do want to record my first differences and my second differences. And I see that my pattern has a linear first difference and a constant second difference. So I know that this is a quadratic function. Recursively, if I want the equation of this function, I'll start my recursive equation. I know that it's increasing, it's adding, and I need a linear expression that represents my first difference. What that means is I'm creating an equation to represent the linear relationship. So I have these x values and then these y values to get an expression for the linear change. I know that my slope for this linear relationship is 14, and I have points, so I can just use point-slope form to write a linear equation. So I'll do x minus 2 plus 21. And now I'll write it in slope-intercept form just to make it a little shorter. So I distributed the 14, and then I'll just combine like terms. So for my recursive equation, I have to get to the next value, I take the previous one, and then I have to add 14x minus 7. And then, of course, my starting value is the f of 1 equals 7. Okay, so this linear expression represents my first difference change. If I wanted the explicit equation, this one is actually a little easier for this relationship because of the way it's grouped. In each one of these figures, I had 7 groups of x squared, which means my explicit equation is f of x equals 7x squared. So for example, here x was 4, x squared, 4 squared was 16, and I had 7 groups. So to summarize, the first relationship that we looked at was modeled with a linear function. There was a constant rate of change because we were adding 5 blocks each time, which meant that there was a constant first difference that showed up in the table. The graph created a line, and the highest powered term was x to the first power. The second relationship we looked at was modeled with a quadratic function. There was a linear rate of change. So in the table, we saw a linear first difference and a constant second difference. The graph created a parabola, and the highest powered term was x squared. All right, that's it for this video. Thank you for watching.